Thank you. So the work I'm presenting is actually part of a larger effort involving a number of other partners. Some are working at fine scale. I'm looking at more of the coarse scale, sub-region level interest in climate change. And I thought I'd just start by pointing out that climate change, it's very, well, it's obviously complex, and depending on how you look at it, it can give you a different perspective. So I'm not a forester, but I'm here speaking to you, hopefully to give you a perspective that will be helpful to what you do and to help enlarge your view of what's going on out there. My frame of reference is this map, the natural subregions of Alberta. I suspect that many of you are familiar with it. And so my question that I sought to answer in the study that I undertook was to say, well, what happens to these subregions through time in the face of climate change? Arguably, this map represents the state of the art in ecosystem classification in the province. I don't think there's a better product out there in terms of defining where the different ecosystems that Alberta has are in space. But what we have to keep in mind is that this is really, it's basically a snapshot, right, as opposed to a movie. So if we roll back the reel and look back in times, in this case around 4,000 to 6,000 years ago, well, Alberta certainly didn't look the way it did today, and that natural subregion map was completely different. Now, we don't have a fine-scale map for the earlier times as we do for today, but work has been done to give you at least a basic idea. The red dots on this map are study sites where people have extracted pollen cores from lakes and small water bodies. And with a core, you can go back in time and get a sense of what grew in that area. And from that, you can reconstruct very coarsely. And I don't take too much from the detail of these polygons here. What I'm just trying to impress upon you is that in the past, we've had, Alberta was at least 2 or 3 degrees warmer, and this is in the recent past, right, 4,000 years ago. We saw the grasslands were up probably a couple 100 kilometers from where they are today. A lot of what's central mixed wood today would have been much more like what we call dry mixed wood in that past time. So again, not dwelling on any detail here, but let's get used to the idea that Alberta has always been evolving in terms of its ecosystem distribution, and it's going to continue to do so. So my interest is going forward in time, and to do that, the first step is to gain an understanding of why are things the way they are today. If we understand that well, or have some confidence in that, then we can predict or try to project what the future will look like. So there, at the fine scale, I imagine most of you are used to working at a stand scale where soils and aspect and various local characteristics are dominant influence on what grows in a specific site. Well, at a regional scale, it's not like that. At a regional scale, there are a few really important drivers that explain, in large part, what we see out there at the subregion scale. One of them, I'm showing here by this arrow, is available moisture. So if you get in your car in Medicine Hat and you drive along roughly the direction of this arrow, a lot of you, I'm sure you've done that, you know what it looks like. We're starting off at a very short grass prairie. Eventually the vegetation is getting a little taller, starting to see a few aspen groves, eventually then closing into a solid forest, and by the time you get up towards Slave Lake, we're looking at a boreal mixed wood forest. The driver behind that is the gradient in moisture. It's getting wetter as we move up in that direction, and it's getting colder. Okay, and that's a very strong relationship. We can feel there's a mechanistic base between the plants that we see and this climatic gradient that's present. It's not the only gradient that's important in generating patterns. Another one is elevation. So as you drive up the Birch Mountains or up into the Rockies, you'll again go through a series of ecological systems And in that case, in this case, we're responding to going up in elevation. Climate doesn't explain everything, this isn't a pointer, but in the far north east, where the shield is, it's actually, in that case, rock, the actual granite there that dictates what grows more so than the, okay. Thank you. In some parts of the province, the soils, like the sandy soils in the Athabasca plains here and in the shield, they are important. But by and large, 80% or 90% of the province, climate is the #1 driver. So if it does have explanatory power, well, then let's have a look at what we have to work with in terms of climate. Here's the mean annual temperature. This one's fairly regular, moving up in bands from a south to north direction. One thing I draw your attention to, maybe you can't read them, but is the numbers here. This is what I've got on here are the mean annual temperatures for the different subregions. The specific numbers aren't important, but what I wanted you to see is that the differences between the north and south are actually not that great when you look at mean annual temperature. So, Medicine Hat is around +4, Fort McMurray is around 0. So 4 degrees can explain a lot of difference in terms of ecological distributions. Even though 4 degrees doesn't really sound like that much, it is a lot when you're talking about annual means. Here's a map of mean annual precipitation. This one is really important in terms of understanding what's going to happen in the future. And what I want to do is draw your attention to the very far north here. Look at that color. It doesn't matter exactly how many centimeters of moisture it is, but look at how it matches this here. And this color here is what we're seeing in this area. So the point I want to bring forward here is that even though the top third of our province is all closed boreal forest, it doesn't actually get more water than we do right here in the Edmonton area. So you have to ask yourself, well, why is it then that that's closed forest and we're here in a grassland aspen kind of mixed ecosystem? And the answer is by and large boils down to temperature. If you're both getting the same amount of water, what's happening in our area here is the hotter temperatures that are driving the moisture off of the ground. It's no longer available to the vegetation. In the north, it's a lot colder. So think of the example of putting your laundry out on the line, 33 degrees in the middle of July. That laundry is going to be dry in an hour. You put that same laundry out in February, it'll dry, but it's going to take a very long time. And that's what's happening in Alberta. And that is going to explain most of what I'm going to tell you and provide for you as far as future projections. There's not a lot of, there's no tricks involved here. You don't have to have a lot of statistical prowess to be able to predict what's going to happen. You just need this map and add temperature and away you go. Last thing I wanted to point out here was climate moisture index. This comes from Ted Hogg and allies that have been working on this for quite a while, looking at the combination of temperature and precipitation. So his climate moisture index looks at the amount of precipitation, subtracts off potential evapotranspiration. And the point I want to make with this map here is, again, drawing to the north, that we're seeing a huge area of the province with about the same color, which means that the amount of moisture is really even over a large area. And why that's important is that once we get close to a tipping point, we have a huge, huge area that's going to be impacted at the same time. It's not the same as in the prairies where you have tight bands where things work a little differently. So, okay, on the left here I have the subregion map again, and on the right I have one of the various regression models that I've used to put these pieces together. So in other words, we know how the ecosystems are distributed in space. We know the climate, and I'm looking here at the past 30 years as far as a reference for climate. Statistically, we can put those together in very simple regression models. There's all kinds of different ways you can do it, but you don't have to do anything fancy. And the reason why I like to use the regression models is because everybody can understand them. We're just looking at basically a linear gradient in temperature and precipitation as we move from south to north. And you know that a lot of these ecosystem lines are essentially the same too. Short grass, longer grass, aspen, forest, and so on. It's not too hard to put those together, and you can produce very easily projections that are highly accurate. So what I'm saying here on this, the map on the right, is basically you give me the temperature, precipitation, and a bunch of other climate variables I put into here, seasonality and so on, and I will tell you with 98% accuracy which subregion you're in. Okay? And when mistakes do occur, they're just at the boundary between one or the other. So we could be quite confident in, for most of Alberta, again not all, but almost all of Alberta, if we know the climate, we can project the ecosystem type. Well, that's good. That's our modeling toolkit for going into the future. There are a couple of assumptions when we go into the future. One is we have to assume that these relationships, like if it's got, you know, if we've got a climate moisture index of negative 15 centimeters, a certain amount of maximum temperature, we're going to have a shortgrass prairie. We'll have to assume that in the future, if we have those same basket or envelope of climate variables, we're also going to see shortgrass prairie. Okay? So to the extent that that assumption holds, we can predict what's going to happen in the future. There are caveats. The main one here is lags. Just because the climate has changed doesn't mean that our ecosystems, it's not like flicking a switch and they're all going to flip to drygrass prairie, right? It's going to take a while for succession to take us to that point. Eventually, when equilibrium establishes, that's what we can expect. But this issue of lags is really a tough nut here because it's hard to put a strict time on it. It's hard to know how long some of these things will take. And, what I'll show you now is some of these projections, and the reason I've taken a little bit extra time in going through this step here of explaining how I've done this all is to give you a sense of where the uncertainties lie, because that becomes really important in what you do about it and how confident to feel about the projections if you kind of understand where the gaps are and what we know well and what we don't know well. Okay, so the last step for projecting into the future is we have to have some sense of where the climate is going to be. That information comes from global climate modeling teams all around the world. There's at least 23 big ones, some smaller ones, and I've got information here from 23 of these modeling teams. This is their projection for the period toward the end of the century, centering on the 2080s. I'm showing here their prediction for temperature and precipitation. There are two groups of data shown here. The light gray diamonds, those are, there's a scenario there of reducing, or not, I shouldn't say reducing, but the scenario of greenhouse gas is assumed to taper off, and that we kind of get our act together in terms of reducing emissions in the future. The black squares are more of a business as usual, where we keep on producing more and more or releasing carbon and really aren't effective in controlling the emissions. So that turns out to make quite a big bit of difference in terms of where we end up by the end of the century and beyond. The rest of the variance between the dots comes down to the different climate models. Everybody's got a different way of putting them together. There's a lot of uncertainty with that. So their predictions don't hover around one point. They're fairly broad. And this graph gives you a sense of how broad. Pointing out a few important things here. First of all of the models, all of them, say that we're going to see at least 2 degrees increase in mean annual temperature by the end of the century. Again, maybe that doesn't sound like much, but again, remember the differences in Alberta are only, you know, a lot of them are explained by 4 degrees. 2 degrees would be the difference between something like Edmonton and Fort McMurray. That's baked in. No matter what we do now as far as climate or greenhouse gas emissions, We can't change that anymore. That carbon is already in the air. Some of the other extremes are, you know, I've got here a median around 4 degrees and a worst case scenario, that pink dot on the far right, of about 6.5 degrees. That probably is as bad as it gets. I'll show you what it looks like spatially in a minute. In the study that I undertook there, I couldn't look at all of the models, so the colored circles just represent the specific ones I looked at. For this presentation, I'm going to focus on the green here. I'm calling this the cool, even though it's 2 degrees, and the extreme over here of, I'm calling that the hot. The other thing to note here is precipitation. So virtually all the models predict we're going to have more water than less, something around 8% on average. So it's not a lot, but it's a little bit more than what we have today. But that water is going to be falling more in the winter months. In the summer, most of the models suggest we'll actually get less water. And again, if you remember my point about temperature overriding, that's critical here. So we have a little bit more precipitation, but a lot more warming. So the net effect is Alberta gets drier under most models. Here's what it looks like spatially. On the far left is Alberta today, with a piece of the United States and Saskatchewan stuck on. The reason I put this here is to provide context. So again, don't worry about what the colors mean specifically, but if you see Lethbridge is this dark color here, what you're seeing in the future is that Lethbridge-like temperature is now going to form a band in the middle of Alberta. That's under the cool minimum 2-degree change. On the extreme, kind of the worst case, we won't find any parallel in Alberta anymore. You have to go to the US. So we're looking at, you know, Lethbridge temperatures up at the, you know, top of the province, and this is kind of, you know, farther down around Wyoming, that kind of thing. Now, in the report, there's pages and pages of these kinds of maps for those that are interested in the details. I'm going to show one here and kind of walk you through it and make a couple of points. With the models, you can project in various ways where the ecosystems will be in the future. I'm showing here the parkland. Okay, so that's where we exist. Edmonton here, I suppose a lot of you aren't from here, but Edmonton's in the heart of the parkland. Let's start with the map on the left. The parkland today is shown in yellow. Okay, that's where we are. What the different colors represent are slices in time of where the parkland will be. So the red is 2020. It doesn't shift much, just a little bit of movement. And again, we're looking just at the cool 2-degree increase here on the left. What we're seeing is that by the end of the century, 2065, 2080s, much of the Peace Country here is now under a parkland climate, and it's moved into a big, following the lowlands basically at the Peace River and Athabasca River by the end of the century. Under the hot model, initially there's not a lot of change, the first decade or two, but then it kind of goes kaboom, and by mid-century already, a lot of the province, northern part of the province, would be under a parkland climate. Again, if you're asking the computer model, given these various climate parameters, what ecosystem am I? And it says, I'm parkland, if you're in these areas here. Doesn't mean it's going to turn into parkland immediately, but it means that under the worst case scenario, that's what the climate will be most like. Okay, so what does that mean in terms of the actual ecosystems? I'm just throwing one slide in here for fun on the southern part of the province. Not a lot of trees there, but just for completeness. When I talk to some people, I sense that, well, we're going to turn into a desert, and that's probably a gross overstatement. Under the least change, we're looking at, what I've got here is the vegetation types of the U.S., and what's important is what's going on right here in Montana. We share a lot of those grass species. Over half of them are the same, actually more like 3/4. And so as some of those species move up, or grasses move up, they're already here. Eventually things like buffalo grass and so on will move up, but under the least change scenario, it doesn't look a lot different. The grass species will eventually be a little different, but most people frankly wouldn't notice. Under worst case scenario, you do have to go a lot farther, and you would see species we're not used to here, different kinds of sage, for example, and so on, but it's a long ways from turning into a big desert. Even under the worst case scenario, people in Wyoming get by just fine. It does imply a lot of change into what we do on the land. Anyway, let me focus more on the forest side, and especially the boreal, because that's where the big changes come, and that's why I spent a lot of time on that precipitation map, because it's so close to the tipping point already, it doesn't take too much for a big change to happen. And it's a lot of the province, right? It's the largest natural region by far. Okay, back to this issue of uncertainty. What I've got here is, again, all the different climate model projections, put it forward. And I'm looking at specifically the moisture index. Okay, back to Ted Hogg's work that says there's a tipping point, and after you get to a certain point, something around zero, where, in other words, the amount of precipitation equals the amount of evaporation, that's kind of roughly the place where you start to see forests. Or put it the other way, if it gets much drier than that, forests can't be maintained over the long term. Where we are at today is shown by the black line. Okay, we're here at this black line today, about a +4 for the central mixedwood subregion. And we've got forest. It's not that far from zero. If you look at what the models suggest for the 2080s, there are some models that say we're going to hold our own or even increase. I will point out that this one that shows a lot of increase, it means a lot of more moisture. In other words, in this model, the amount of extra precipitation overwhelms the temperature. That's the Russian model, and there's not a lot of faith in that model, frankly, but it's out there, and you can't entirely discount it. The vast majority of the models show that the mixed wood is going into a moisture deficit situation. Again, you don't need anything else statistically or fancy model-wise to tell you what's going to happen. If you're in a moisture deficit in the boreal, how can you maintain a forest? You can't. The question is only, how long is it going to take? Now, I skipped over the various maps that I have in the report, but the message in them is that the general trajectory of change is fairly consistent among the different models. Where the differences lie is in how fast the change occurs and how far it goes along the way. The least change model will stop at a certain point, whereas the worst case keeps going and going and going. Okay, but the trajectory is similar. So in these maps that I show you here, I'm just going to, you can interpret it as this is what will happen under the cool model, or you can interpret it as this is the first stage of change under the worst case scenario. They're both the same. So the first step is a transition, or I'm just going to kind of move around the landscape. I'm pointing here first at the dry mixed wood. And what happens there is, quite expectedly, we're going to see transition to a parkland. It very quickly, even under the least change scenario, is subject to a parkland kind of climate. Now, there is going to be, as I said, a lag, and that lag will have to do a lot with the mature trees being able to withstand climates that they're not necessarily, that the climates are not ideal for them. But that doesn't mean that they roll up and disappear, right? We've got shelter belts all over the southern prairies that are, the trees are growing there that arguably shouldn't be there. But if you hand tend them and plant them when they're young, once they're mature, they can withstand a lot. So that's the case that's we have in the north. The mature trees will hang on for a long time until disturbance knocks them out. So long as the climate is suitable, like if a fire comes through or a drought comes through, they will regenerate, right? They'll come back. They always have. That's what we're used to. The difference is that once the climate flips to the point that it's no longer suitable, the regeneration path is now going to be different. And in the case of the dry mixed wood, where you got a dominance of aspen. It's probably drought situations that we're looking at causing a change. We already had in 2001, probably a lot of you are familiar with, we had a large die-offs. Again, Ted Hogg did some very good work in documenting that, and I think it was over 30% mortality of the aspen in this kind of southern dry mixed-wood fringe there. Will it come back? Well, probably it actually will, because we're not yet in a climate place where regeneration can't take place. But eventually, I mean, you know, you can't grow a big aspen forest when you have a parkland or even a grassland kind of climate. It won't work. Next, looking at the central mixed wood, and similar to what we saw in that hypsothermal 4,000 years ago, we're expecting a transition of central mixed wood into what we currently see in the dry mixed wood areas. So here, more than anything else, we're looking at a loss of the spruce component. Why? It's that initial phase. If you've got 3 really dry years, those seedlings are just not going to make it. It's not a uniform thing. It's going to be really patchy, right? Because you can have good years and bad years. But overall, under the default condition being, humans are not out there, you would expect to see a progressive loss of the spruce, because every time they're taken out by fire or other disturbances, the regeneration won't be there. The aspen will come on strong, and eventually you'll have more and more of a dominance by aspen. The big overriding issue here, of course, is that the forests aren't just on their own there. As we harvest, we replant, and replanting can skip that vulnerable seedling stage. So it becomes actually more of an economic issue. At what point in time, does regeneration failure become an economic problem, or does, if we have a double or triple rate of fire in the second half of the century, how many times can we afford to have the stands wiped out before we're able to harvest them and still economically have a viable industry? Those are the kinds of issues that I'm not going to address today, but will be facing the industry. But my projections here are all regarding what will happen kind of in a neutral default case. So here's the point being central mixed wood having this mixed structure and transitioning to a more aspen-dominated forest. The other point to make about the boreal is the peatlands, right? I mean, they're 45% of the central mixed wood is underwater of some kind or other. And if you look at the dry mixed wood, it's down to 15% peatland, and parkland 10%. So again, without any fancy statistical models, if central mixed wood has now got the climate of dry mixed wood, why wouldn't you expect those peatlands to transition into something else? I can't think of any reason why not. The big question is, how long will it take? Peat acts like a sponge, right? So even though there may be less water and it may be somewhat more sporadic, every few years it is going to recharge, and it could end up taking quite a while. Eventually, though, if we reduce the amount of precipitation that's available, I mean, precipitation's coming in, but it's being driven off faster. Okay? So there's less water that's surplus, put it that way. If that water declines, it's not going to be there to keep those peatlands wet. The vegetation from the sides are going to move in. Arguably, at some point, it could be a tremendous amount of new mesic habitat for growing trees. I don't know. I haven't been able to find anybody to answer that question for me. It's an area of research right now to understand what the dynamics might be. Fire probably is going to be important. If you have, let's say, 5 years of quite dry conditions, that peat would be very dry, it'd be susceptible to burning. After it's burned, there's no longer a sponge there, and you could transition to just an ordinary wetland. Those kind of questions are open right now. Anyway, by the end of the century, under the least case scenario, we'd be looking at a dry mixed wood kind of forest. Under median to the worst case, the transitions would go How far is really hard to say. It certainly will not, by the end of this century, be a parkland or a grassland out there, no matter what. On the worst case scenarios, it's just not going to happen. Even if you double the rate of fire, those mature trees are standing there. You still have half of the trees present. It also is going to be really patchy because there will be periods of good years where you're going to get good seed crops and seedling production, and other years where there will be a wipeout. So you're going to see some kind of a very complex, patchy structure as we have small patches of grasslands around the Peace Country, for example. They will expand, aspen will dominate, but it's going to be very hard to predict the patterns or how fast. It's just we know the trajectory is going in that direction long term. Last point here is in terms of what happens to these hill systems. This is where, even though we're going to be losing central mixed wood in the lowland areas, right now these highlands are quite inhospitable. A lot of black spruce and scrub up there, a lot of permafrost. Those areas, they're going to melt and eventually become quite suitable. Aspen is not found up there, it's too cold, but it's going to be moving up. And again, it's really hard to know the timing because the first stage of transition is going to be, it's going to get actually wetter, right? When the permafrost melts, there's a tremendous amount of water that's going to be there. That stage has to be gone through before it turns into a more music habitat for trees to grow. Okay, finally moving into the Rockies and the foothills. The basic transition there is very easy to understand. It's already happening now. Ecosystems just wholesale going to move upslope. We're already seeing aspen growing at elevations that they've never been seen at, and that is going to continue. They will not, however, move as solid units, so it's not like the upper foothills is going to move as a chunk straight up. You'll see a blending of different species. Like I said, aspen's already starting to encroach in upper foothills. The definition of upper foothills is where you don't have aspen. Well, how do you draw the line? The little places here and there start having aspen. It's all going to blur, but generally moving upslope. Important point is that there's really a difference here compared to the boreal because the foothills and Rockies, they're very wet, right? They're not close to that tipping point that I've mentioned is so important in the boreal. So even though we're going to warm it up substantially, it should not be getting close to the point where moisture limitation is going to reduce the amount of forest that's present there, with the exception of lower foothills, which I'll come to in a minute. There is a lot of uncertainty in regards to what happens in the lower foothills. There's two possibilities. You can have central mixed wood kind of moving in this way from the north into the foothills, but you also have the possibility, particularly around here, of seeing parkland and even some of the fescue grasslands moving in, and this montane down in this area here quite likely will be moving up in this direction here. So what's actually going to happen in the foothills, it cannot be predicted statistically because there's too many possibilities. All we can say is it's going to be mixed up. There will be some areas encroachment of grass and parkland, especially on the south, but the rest of it, very, very hard to predict. Essentially unpredictable, but it will not stay the same. You may have more boreal, central mixed wood character, something in between, hard to say. This slide came from another presentation. I just want to make one point with it. That's with regards to the mixed wood old growth. From the perspective, at this stage in the presentation, what I should switch into is say, here are impacts, and this is what the forest industry is going to face, because I've alluded to a few, and there are a whole bunch of them. That's not my area of expertise, so I'm hopefully somebody else will backfill that. I know that the Canadian Forest Service has a roadshow they're taking around on this issue. So there are a variety, but I'm not the person to speak to them. I just want to point out the issue around old growth forests, because from an ecological perspective, that's where many of the vulnerabilities lie in terms of the species that are most at risk from human impacts. The issue being, if we're losing or transitioning to dry mixed wood, the first thing to go is going to be the older stands. We're ramping up the rate of fire by at least doubling, quite easily tripling the second half of the century. We're not getting the regeneration. It's going to be a real struggle for those species to carry on. Arguably, they will be, as the central mixed wood moves north into this area and it moves up in the hills, we should see old growth in those areas eventually, but there's going to be a bit of a bottleneck because you can't go from black spruce permafrost, conditions to old growth forest. It's going to take a very, very long time. And down on the lowlands, with increases in fire and potentially drought and so on, we're going to lose it faster. So just to bring that as a point. There's another issue is the non-native grasses, all the seismic lines, the right-of-ways for pipelines and roads and so on. They've been planted for years with agronomic grasses. Now, studies that have been done have suggested those grasses have not been moving into the forest. So long as there's forest there, they can't really make it. They're staying on the right-of-ways. But now you put in, change the climate such that the climate is actually most suitable for grass. It's not suitable for, at least not suitable for regeneration of trees toward the end of the century. What's going to happen with all those grasses spread everywhere, right? There's not a place you can go in the boreal that doesn't have some seismic lines with grass on them. And so a big open question of what's going to happen there. Okay, just to wrap up a few slides on implications. One is once we start changing the climate, it makes us, we have to go back and have another look at what are we trying to achieve out there. And again, I have a few examples on the forestry side. Most of my examples have to do with specific wildlife species, so I have a limited number to draw on. This one, Arctic grayling is really good for this point, but so just bear with me. What we've done in the past is basically assume that our objective is to keep things the way they are. We like things the way they are, and we're going to go out into the landscape and do various kinds of activities. But over the long term, we want to keep things the way they are. So we've set up various objectives that are essentially static, and they're usually spatially defined. So that 100 years from now, let's take Arctic grayling for example, the objective is we want to see Arctic grayling in all those streams just as we have now, and have all our fishing opportunities and hunting opportunities and so on just the way they are today. However, I use this example because there's a very direct and link to temperature, right? As temperature goes up, the water goes up really, temperature goes up right away, and fish experience it much faster than some of the other species. The black dots here show the location of populations that are already in decline. Now, according to our current set of objectives, we have to keep things the way they are. It means that you have to go and spend the bulk of your conservation efforts or management efforts on those species because they're the most in trouble. You've got to keep things the way they are. You've got to put your effort where the trouble is. But if you put this forward 50 years or 100 years, there's no way that these populations are going to be here anymore because they cannot survive. The physiology does not coexist with the water temperatures that we're going to see there. So it doesn't make sense to keep a static objective. Arguably, no. Arguably, we're going to have to start looking at making our objectives dynamic. We cannot, there are things we can do to reduce the amount of warming that will happen in the future. Prevention is an option for us as a global society, right? But once the climate changes, it's already gone up by a degree, you cannot turn that clock back. That's going to be with us for several thousands of years. If it goes up by 2 degrees, we got to live with that. So the idea we're going to fight it and we're going to keep things the way that they are today, it's just not going to hold water. We can slow it down perhaps, and in many cases that does make sense, but we cannot stop it. And so what I'm suggesting here is that we're going to have another look at our objectives and start to think about what makes sense in a world that's constantly changing. And static objectives are going to have to be more dynamic. We also have to be careful about not doing things today that are actually contraindicated or actually make things worse in the future. For example, if we're undertaking reclamation of the oil sands, I mean, right now in law, they've got to put things back the way they were, right? That is the objective. Well, does that make sense? Already, work by Andreas Amann and Laura Gray have shown that there's something like a 100-kilometer shift in the association between climate and current forests. In other words, the trees that are growing today, they're already 100 kilometers out of their optimum range. And that's only going to get worse as time goes forward. So should we be planting trees that are, where they would have been optimal 30 or 50 years ago? Or should we be planting them, what should be optimal 50 years from now? Of course, they won't necessarily grow if you plant them today because the climate is not there yet. But the point is, again, we have to start thinking through these kinds of management decisions and have a more dynamic view of things. Putting back things the way they were is not necessarily going to be the best way of going about things anymore. I'll just end off with just a few implications for planning. As the last couple of examples have pointed out, the decision space that we have to work with is a lot more complex. Life's a lot easier if you can say that, here's my objective and it's for the next 100 years, that's exactly what I want. And how do I get it? What's the best way of getting that objective? Now, if the objectives are constantly shifting, if everything's dynamic, you're ending up having to have trade-off decisions. Should I plant a tree that's optimum for growing today, or should I be planting a tree that's optimal for growing 50 years ago, from 50 years from now? They're not the same thing anymore, so you have to make decisions. There's trade-offs to be weighed and taken into account. So life is becoming more complex that way. You also have a lot more uncertainty. Now, uncertainty is not new, but we've always had to work in the context of uncertainty, but it's certainly an order of magnitude greater than it ever has been before. I think when you compare the least change and the worst case scenario that I've presented for you, well, I mean, how do you deal with that as a manager? Which one of those outcomes is the one that you should plan for? There's no way to know at this point which of those models is more reliable than the other. There have been some tests, to look at their ability to predict, but there's really no gold standard. Really, there's no way of knowing which of those models is the, quote, giving the prediction that's going to be the one we're actually going to experience. So at this point, we're faced with a range of possible futures. And the only recourse that we have is to use scenario modeling. I've given you a variety of outcomes. There are others in the report, and other people are working on other projects that are similar to it. From those, I would suggest none of them are reliable as a forecast. None of those are useful for you to say, okay, this is what the climate of the future is going to be in 2080. These are the trees I'm going to plant, or these are the fishing objectives I'm going to put in place. You can't do that because you don't know which of those climates is going to be the one we have. So that means that we have to start looking at different ways of planning, different ways of optimization. So the way we do things now, I've labeled here as deterministic. And here's where forestry is a good example, right? We have an inventory, we know what's growing today, we've got permanent sample plots, and from that we derive growth and yield curves, so we have a pretty good sense of 50 years from now and 100 years from now exactly what that forest is going to look like. And then we can decide, which stands are we going to harvest? Should we go close to the mill or far from the mill? There's trade-offs there. We can assess those different strategies and say, well, this makes sense here, but overall, I've got these different levers I can pull. This is the best choice that I can make in terms of decisions, management decisions, to get me the various objectives that I have, maximize timber flow, reduce costs, get some biodiversity objectives maybe at the end of the day. But here's the different levers I'm going to pull that'll get me there. And I've taken time and effort to determine which of these different levers makes the most sense, which does the best job after assessing all the trade-offs, all the costs and benefits. That's all based on being able to predict the future. You have to, with some confidence, say, yes, I know what the forest is going to look like 100 years from now. Then I can go and optimize and get there. I've just told you you can't do that anymore. So now where do you turn? There are new ideas, or maybe not even new, but they're applicable here now. Some of them go under the heading of robust planning. So instead of saying, I'm going to seek the best management strategy for this outcome, you say, well, look, I don't know which outcome we're going to get anymore. So what may be best for outcome A, let's say the least change scenario of climate, may not be the best choice of strategy for the worst case outcome or the one in between. So instead of trying to get the best, you have to start looking at the different scenarios, and there are different ways that you can do this, but they call it the no regrets. Which strategy is best in terms of, or least bad, in terms of achieving your outcomes across all the potential outcomes. I won't go into any detail here, but there is quite a bit of work on this coming out right now. The other approach is, I've labeled here under bet hedging, but it's basically not putting all your eggs in one basket, again, because we can't predict which of the futures will be the one that we'll experience. Let's try different things in different places. And there's a lot of parallel here to adaptive management in its broadest sense. We're going to try different things in different places and learn as we go which ones work and which ones don't. We may also use a bit of a shotgun approach, like instead of, I guess I've heard some examples in the context of forestry, instead of replanting always the same kind of stock in every area, using more of a portfolio of different seed stock and species mixes and genotypes and so on, so that something is going to come through over the long term. Finally, I think a way forward is to start thinking about planning in different timescales. Like in the short term, next 20 to 30 years, deterministic planning should still be reasonable to do. The uncertainty that exists is manageable, even though I showed you a big scatter plot of outcomes at 2080. When you look at the next 20 to 30 years, there's a lot of model agreement. And the amount of change is not that great. It's only about a degree increase. And the amount of ecological change is not that great either, because there's a big lag in the system before things really start rolling. So you can still make today, even fully accounting for climate change, quite reliable predictions 20 or maybe 30 years out. And the current way of planning should still work quite fine for that time period. But I think there's going to need to be a change for the period after 2050. And of course, that does include some of the long-range forest management planning that is done. I think there needs to be a transition to accepting that we cannot depend anymore on the forecasts that we have. The timber supply models going out 100 years from now, I just can't see that they're reliable enough to really depend on. At a minimum, there's going to be a need to look at the alternative scenarios and start to move to more dynamic objectives. The long term is unfortunately just going to be a little bit more fuzzy in terms of what we hope to achieve and what we can achieve than today, where there's more of a feeling that we can be more clear about what we want to achieve and how to get there. And it'll be a little bit more broad than that. And with that, I'm finished and be pleased to answer any questions that people may have.
One of your very first slides there, you said that the temperature was warmer about 4,000 to 6,000 years ago.
Yeah.
What causes it to cool?
It's a lag effect. So the whole thing that's going on there is the glacial cycle. Like we've gone through many glaciations, and that has to do with the Earth's orbit around the sun. It's not a circle, it's an oval. There's a variety of things that tilt and so on. The point is that 11,000 years ago, we were at the solar maximum, where it was actually the most sunlight energy hitting the Earth compared to the previous glacial period. But we were underneath 2 kilometers of ice. So even though there was more sunlight and energy hitting us, it wasn't warm at that point. It had to melt the ice first. And that took a while. So there was a lag, but the point where you actually felt the temperatures being the warmest was near the solar maximum, but it was a couple thousand years after that because it had to wait for all the ice to melt. So it's just a long curve. The solar maximum was about 10, 11,000 years ago, and there's a slow decline, which we're still in today. And without climate change, with 30,000 years from now, we'd be actually in the next ice age, right? There's a tipping point where that happens. So it was warmest 6,000 years ago only because there was ice in this early period that was reflecting sunlight back, and that cooling that ice required took time.
Richard?
Hello?
A couple questions. I noticed on a few of the slides that the west central area of Alberta wasn't modeled or predicted. Why was that? And the second question is, in terms of the modeling you've done, there's this kind of doom and gloom moving forward when we see this climate change. Does any of the models accommodate some sort of reversal of that? So, we get our act together, we start doing things to affect our CO2 emissions and then reversing that. Is there any work on that where we might go through a period of climate change but reversing that back to more traditional representation of that?
So should I address that one first or the other one?
Whatever you want.
Okay, well, the first one on the foothills, I did model them. I didn't show them. So what I did is I broke the province into pieces for the modeling because it was better to do that, and it was like the associations are tighter if you work with places like working with the moisture gradient that goes from the dry grasslands into the boreal, a really tight association between climate and vegetation there. It's a different pattern going uphill, so I use a different model there. So when I showed it blacked out, it's just I couldn't show you all the models. They're in the report. That said, the West Central is the hardest to model, and I say so in the report. I do not have any confidence in any projections of any model for that area, because the computer can give you results, and I show them, but I still don't believe them, because the whole way that the models they work is by saying we're looking for correlates somewhere else in the province that have similar temperatures today, and the foothills will have that temperature tomorrow, so we can assume it'll be like that. But the fact is, there's no place in the province today that's as wet and as hot as the future foothills. There's no correlate to that anywhere. You have to go to Minnesota to find something that looks like the foothills in the future. So and then I said there's more than one direction. You could be having boreal coming in from the north, or parkland and vestry coming in from the south. It's really, really hard to know which of those. The models can't separate that out for you. It's hard to know which one will dominate. So it will change. It will be a mixture of species, but how exactly it will change, I do not believe anybody can predict. The second point being, what about if we get our act together globally and reduce CO2 emissions? That actually is reflected in the, there's a, maybe easiest to do it here. Yeah, the B1, the pink scenarios, are under the assumption that we get our act together. Okay, so there is no better case than that. The reason is that there's so much CO2 in the air already that those effects are baked in. Regardless of what we do in the future, you cannot, well, right now we do not know of a way to scrub that CO2 out of the atmosphere. The reason we don't instantly see it is there's a lot of lag in temperature too. Like right now the ocean's sucking up most of the heat, but because carbon is there and it will take its effect. So you have a big difference in terms of whether the boreal stays as an intact forest, arguably maybe with less spruce in it, or if it turns into a grassland. That will depend on how much future CO2 we emit. But you do not have the choice of doing any better than the best case scenario that I've showed you, which implies a dry mixed-wood transition in the central mixed-wood. That is guaranteed. The only proviso I put on is I'm not sure how long it will take. Will it be 50 years or 100 or 150? That is where the uncertainty lies. None of the models are in disagreement about that. Probably the biggest issue where there's uncertainty is how much more moisture The models are really strong, and it's basic physics. You put carbon in the air, it's a blanket. There's not really a lot of question about, the warming. It's the precipitation. And there are a couple models, as I showed you right there, right, that say, yeah, it's going to warm. Those models also suggest warming, but they say there's going to be so much more precipitation because the heat drives it off the ocean. You've got all this water in the air, it's going to fall down somewhere. If it falls down in Alberta, it could be wonderful. We could be Minnesota, warm and wet. Is it likely? No. Are we done?
Thank you, Dr. Schneider. You've given us a lot to think about. Our next speaker will be Dr. Aaron Bain from the Associate Professor Department of Biological Sciences at the University of Alberta.